So, this first presentation, it's a general overview of the project. As I said just before, this macXimal project is funded by the European Commission under the Quantum Initiative. And I'll give you an overview of what we did. We are now at the end of the project, so it will end in July 2022. So we had the final meeting yesterday, and we presented all the results. We are finalizing now the deliverables and slowly closing the project. So the agenda of my talk would be first an introduction with a video. So it's a video that we prepared from the whole consortium and the whole project. Then showing you the 14 partners, the 5 applications that we targeted in the project, and beside the application, also the quantum enhancements strategy that we have put in place for future quantum sensors. Then an overview of the results, the results that will be presented within this symposium. You will see that all the results, they will be shown in the different session, and at the end, a closing remark on next steps. So, I'll show you the video.
In recent years, a global race has begun to exploit the enormous potential of quantum technologies. As part of the European Union Quantum Technology Flagship, the macXimal project is built around the use of atomic vapor cell to develop a new generation of highly precise sensors called quantum sensors. These sensors are to benefit the whole society in many different applications. The project, coordinated by CSEM in Switzerland, brings together 14 partners from 7 European countries. Its main objective is to make the European quantum industry stronger by bringing the academia and research and technology organization to work hand in hand for, and even more important, with the industry. The macXimal project is built all around one single basic building block, the atomic vapor cell. In other words, the container in which our sensing atoms are confined.
The quantum sensors developed within the macXimal project require a high number of rubidium atoms held under vacuum in the cells in order to avoid chemical reactions of the rubidium atoms with the oxygen or water in the atmosphere.
CSEM has established and optimized a patented fabrication process to produce atomic vapor cells in a reliable and industrial way based on micromechanical systems technique. This technique is identical in terms of equipment used and fabrication processes to the technique used in foundries all over the world to produce integrated electronic circuits. Hence, we can produce a large number of vapor cells at once on a single 150 mm diameter wafer.
Quality, reproducibility, and tracking are key aspects in the fabrication of MEMS atomic vapor cells for industrial and research applications. At CSEM, we develop an automated cell activation and characterization piece of equipment. This laser-based system can be programmed to UV activate and characterize hundreds of cells on a single wafer in a fully automated way.
Whether it is an atomic clock, a magnetometer, or a gyroscope, a common vision of macXimal is to make high-performance atomic sensors mass-producible, so we can make thousands to millions of units in an efficient way.
Okay, this was the introductory video. I hope you enjoyed it. And we give the floor to what we want to do in the macXimal project. So, as said, I will present you the partners that are making the consortium. So we are 14 partners. You see them in different colors here. So we have first 8 academic groups. So we have IFO in Barcelona, we have NBI in Copenhagen, CNRS LKB in Paris, we have the University of Aalto in Finland, we have the University of Basel in Switzerland, University of Durham, United Kingdom, University of Stuttgart in Germany, and the University of Neuchâtel in Switzerland, where we are today for this live streaming. Then we have 4 SMEs and industry. we have Axelement AG from Switzerland that makes the coordination or helping the coordinator to make his job, and they do a good job. And then we have 3 industry. We have Robert Bosch from Germany, Megin from Finland, and Orolia Switzerland from Neuchâtel. And the goal, then we have 2 RTOs, so CSEM as a coordinator and VTT in Finland, also an RTO. The goal is to really to bridge these 2 worlds, so the academia and the industry, and this is really the role of the RTOs, to bring what is developed in the academia to go in the direction of the industry for further commercialization. In brief, the objective of macXimal are twice. There is one, which is called bring first-generation quantum sensors as close as possible to the market. So you will see afterwards that we target to have 5 applications, real applications, and for this application, we have also industry partners, and for them, the goal was to make prototypes or demonstrators that will be turned afterwards in products. So it's also the goal of the Quantum Flagship to help the quantum industry to bring the first quantum sensors and other things towards commercialization. Then the second aspect in the project is to prepare the second generation quantum sensors thanks to quantum enhanced performances. This I will not show too much in my presentation today, but you will hear about that during the symposium in the different sessions. As you've seen in the video, in macXimal we have 5 applications, and you will see these 5 logos that are representing the 5 applications. We have optically pumped magnetometer called OPMs, atomic clocks, gyroscopes, atomic gigahertz and terahertz sensors and imager, and Rydberg-based gas sensors. A bit in more detail, so the first application, perhaps I will use a pointer here so I can show you the things. So the first application that we see here with this logo here, it's an optically pumped magnetometer for magnetoencephalography or MEG applications. So currently the gold standard are squids-based sensors. You see this big head that is above a patient here, and this requires liquid nitrogen cooling and a lot of maintenance, and the goal is to replace this kind of equipment with something based on optically pumped magnetometer that we could put on a helmet around the scalp, avoiding this cooling and this maintenance of this equipment. Then we have a second application, this one with this logo, atomic clocks. So the company SpectraTime, so Orolia now in Neuchâtel are commercializing clocks. They are providing the clocks for the Galileo system, for example, but they are also in the portfolio now compact atomic clocks like the MRO50, which is the first commercial compact clock with good performances in Europe. And the goal is to even continue the miniaturization of this clock and to make a chip-scale atomic clock out of this compact clock. Then we have a third application with this logo here, the logo of the gyroscopes. This is for the company Bosch in Germany. So currently, autonomous cars are using MEMS gyroscope, and the performance of this MEMS gyro do not allow for sufficiently long performances that allow for driving or making emergency stops, for example. And the goal is to replace at some point this MEMS gyro by atomic gyroscopes that have much better performances. And then we have the 2 last applications. These are the logo for the terahertz and gigahertz imager and sensors. There we have partners like Rode and Schwarz that might be interested also in making a spectrum analyzer, for example, based on these techniques, always based on atomic vapor cells. And there are other applications also for security, example, with the terahertz images. And the last one are Rydberg-based gas sensors, mainly used for nitric oxide measurements. This is what we proposed in in the proposal that we submitted to the EU, so that at the end got well evaluated and got funding for this project. So the goal of macXimal is really to use a central building block, which is the atomic vapor cell here, and to use them in the different applications and to make quantum sensors based on these vapor cells. We see that a little bit more in detail here. So there are different types of atomic vapor cell, but all of them, they are used in the different sensors. This is, for example, the setup for the terahertz imaging. This is an idea of a cavity magnetometer. This is a magnetometer. This is the atomic clock. You see the cell here in the central parts. You have here the setup for the gyro. You have a design for a miniature atomic clock, so even smaller than what we did in the project. This is for the gigahertz sensor, and this is for breath analysis. All of them, they are relying on hot vapors. In the project, we followed a V diagram for the developments. So we started with a requirement. So if I start first, what we did is an IP analysis. So this is really important if you want to go to commercialization, that you look at the freedom to operate or the status of the patents on each of the different application fields. That's what we did, and we did that all over the projects with newsletters that are informing on what's going on the IP. Then we went through this V diagram, thanks to Sylvain. This is a trademark from Sylvain on this V diagram. Requirements, design. Then from the sensor design, we made the cell design, and then there is a turning here. We fabricate the cell, we test the cell. If they're not good, we go back to the design, again to the fabrication and testing. And when this is done, then we go to implementation or integration in the sensors, and at the end, testing and validation. And now we are in the process of finalizing the testing and making the assessment of all the results we obtained in the project. As a summary of what we did in macXimal, and these are the highlights and the challenges. So the highlights, I would say, from the project, as it is based on vapor cell, is the fabrication of this vapor cell in a reproducible way, targeting high-performance vapor cells. And especially, we need the high performance for high TRL application, like the atomic clocks. What we did in the projects are to build prototypes for high TRL applications. That was obtained for the miniature atomic clock, this MAC, and for the OPM, these optically pumped magnetometers. For the gyro, the objective was to make a demonstrator at a shoebox size, and this is realized mainly by Bosch. And the goal is to make first rotation measurements that show that the proof of principle of this atomic gyro is successful. Then the decision will be made to go further and to make something which is integrated and with reasonable size miniaturization. In the project, we found out also a new application that was not foreseen at the beginning of the project. This is a demonstrator of a spectrum analyzer based also on atomic vapor cell. And this is mainly an application that might be useful for our further partner, that is Rohde & Schwarz. And then there are a lot of demonstrations, a lot of scientific work, academic work mainly, to see the potential of quantum enhancements of these sensors. And there are a lot of publications that came out of the project, and this is a big highlight also for the project. There were some challenges for sure. First of all, the whole consortium is somehow not so easy to handle when you have so much different applications, but I think we did pretty well. And there are also technical challenges. So the technical challenges were mainly for the vacuum encapsulation of the different applications, mainly vacuum encapsulation of the cell parts for the gyro, for the atomic clock, or for the OPM. And this is pretty difficult to achieve, and we are still working on it to achieve this vacuum encapsulation, which is needed for this kind of sensors that are based on hot vapors. So hot vapors means you have to heat them, and heating means power consumption. And if you want to decrease the power consumption somehow, you need vacuum encapsulation. Then from the laser point of view, so in Europe, there is a lack of VCSELs at the right frequency. So mainly we are using rubidium in our sensors, and VCSELs at 795 are not available in Europe anymore. They were. And so we are still relying now on international providers, and there should be a work dedicated to this development so that we can ensure providing these VCSELs from European countries. And at the end, one of the challenges and in the project was the association of Switzerland within Horizon Europe. So as we are providing the core element of all these sensors, somehow now to be not able anymore to participate to the next step of the flagship, make some troubles, but still we find solution to continue the work and to help our partners developing these sensors. In these highlights now in images, and I will show you these different highlights showing how they will be treated in the symposium in the different session. So as I said, the central elements of the whole project are the atomic vapor cell. You see different vapor cell here, and you see the wafer level fabrication of these ones. So the next talk that will be following my talk here will be given by Thomas Overstolz mainly, and Christoph Affolderbach and Robert Löw. And they will show you the different kind of cells that we were able to fabricate in the project. This will start just somehow at 11:15, something like that, and last until noon. Then we have in the session 2 the atomic clocks. So you see here the physics package of one of the atomic clocks that we developed in the project. You see here also an application-specific integrated circuit that can be used for driving the clock. And there we have two talks. One talk from Orolia, where we show how from a previous development and from the compact clock that is a commercial from Orolia, we bring them together, we merge them, and we make a new sensor that combines the benefits of both of them. Then we have a talk by Christoph Affolderbach, mainly on double resonance Ramsey interrogation, and he will show the limits that they achieved with this kind of clocks, which has much better performance than the small ones, which are also bigger ones. So we have to combine small size and performance, and these are for the future clocks. Then in session 3, we will have the gyroscope. You see here the design of the prototype that Bosch mainly is building. You see here also the integration of the atomic vapor cell and the ceramic package, which is around, which was developed by VTT. I said we will have two talks, one from Janine, showing this development for this shoebox size atomic gyro, and Marco from VTT will show you the potential of LTCC, this low temperature core-fired ceramic, that can be used in the different sensors for integrating the cell inside these sensors. In session 4, we'll have the OPM. So you see here part of the demonstrator. You see the atomic vapor cell here, some 3D printing that we did for optics adjustments, and also here the special coils that were developed in the projects by the Aalto University mainly, also with simulation software which allow to make new types of coils that can provide the magnetic fields that we need for driving the magnetometer. We'll have 3 talks, one by Kostas. He will show you this development of this OPM sensor, and then 2 talks, one from Rebecca from Copenhagen on conductivity measurements, and a last one by Gian Vito radiometers. This is this picture here. Then in session 5, we'll have mainly the terahertz and gigahertz images and sensors. You see here an image of the results we obtain for a spectrum analyzer based on this atomic vapor cell. And this was done by the University of Basel in collaboration with Rode Schwarz. So both of them will talk. We will have a first talk by Matteo Fadel, and then a second one by Thomas Ruster. And the last highlights and the session 6, this will be on Rydberg-based gas sensors. So you see here a typical instrument that is used for breath analysis of nitric oxide. And they will show you how we have to turn from, I hope that you see still something on the screen. I think we have some issue, but if you could put on the chat if everything is working well, that would be good. And don't forget to ask questions in the chat. So I come back to what I said. They will show you how much volume you need for the breath analysis with standard instruments. And then we have to find ways to improve the performance of such an instrument if we want to make some testing of breath analysis on mice, which breathe much faster and with much lower volume. And they will show you how they did that with this kind of laboratory setup with a lot of laser. They will tell you also the big laser they are using for these measurements. This will be the end of the symposium. And with that, I'm going to the end of my talk. As a summary, I'm more than very proud of what we did in macXimal. I want to thank you here, all the partners which are here in the room, and that will continue to speak during the symposium and showing you everything they did during the last 4 years about. It was extremely challenging, and we had multiple and diversified applications, but always relying on hot atomic vapor. And this is our core element, and we love these hot vapors and to build sensors around these hot vapors. I think we reached all the objectives, but there is a small but. This is what I told in the beginning of the talk. The non-association of Switzerland to Horizon Europe causes some more challenges, but as said, we will face them. There is also Switzerland helping us to continue working on that until we get reassociated, and we hope that the reassociation will be effective in the near future, but this depends more on the political aspects and not on scientific aspects. With that, I'm at the end of my talk. I thank you very much for your attention.
So good morning, ladies and gentlemen. It's a pleasure to me to introduce you in the work that has been done around the fabrication of the vapor cells that Jacques mentioned several times. During this project, and already in some cases before, at CSEM we have manufactured many different types of vapor cells, most of them based on MEMS technique. There is one example where for University of Stuttgart we made also a MEMS cell, but which was afterwards bonded to a very thick glass piece because they needed to make a filling which is different from ours. Here we have an example of a vapor cell as we produce them for the application in atomic clocks. You see here the rubidium that condenses on the surface of the glass window. There are resistive heaters around which allow to heat the cell. This is on both sides of the window, on the back side and on the front side. And they have also here, they can accommodate a NTC temperature sensor to monitor the temperature. Then we have also one example of a cell where it was filled with a rubidium pill, which was activated afterwards by laser to give the rubidium vapor inside the cells. But most of the work we did here at CSEM is based on on the fabrication with rubidium azide. Here you see one example of a cell that is used in the OPMs. This is a cell with two different chambers that are separated by a small narrow trench. And here you see a lot of rubidium that condensates in this filling chamber, but there's nothing in the science chamber, which is very good. So we want to avoid rubidium sitting on the glass, because we have to go through with a laser to probe the rubidium atoms. So vapor cells are very often filled either with rubidium or with cesium. Rubidium, cesium are elements of the first column of the periodic system. They have only one valence electron, and this makes it spectroscopically much more easier to work with if you don't have to handle with many different spectroscopic lines. One issue in fabricating a vapor cell, or stay around, the most straightforward idea to make a vapor cell would be taking a wafer with a cavity going through, putting a glass window on the backside, putting the rubidium, the metallic rubidium inside, and then close the cell with a topside glass. Unfortunately, alkali metals are very good oxygen getters, and once the rubidium or cesium is oxidized, it is not available anymore for spectroscopic application. So this fact makes the filling with directly with metallic rubidium or cesium very cumbersome, because all this has to be done under very high vacuum conditions. So that's why we came up with another idea. We still start with a silicon wafer where we etch a through hole. We put a glass wafer on the backside. But now we do the filling instead of metallic rubidium with rubidium azide. Rubidium azide is a salt. It is very good soluble in water and can then be printed or spotted. And the big advantage of working with rubidium azide is that this salt is completely inert under normal atmospheric conditions, so it will not react with oxygen. Then, once we did the spotting, we closed the vapor cell with a glass, and then we have to make a decomposition, which we do with a UV irradiation, and upon this decomposition, we decompose the rubidium azide into metallic rubidium and nitrogen. And the nice thing about this process is that, at least in some of the applications, these vapor cells, they need a buffer gas inside, and in many cases, the buffer gas is composed of nitrogen and of argon. So in this case, we do the bonding at the end where we close the cell with under argon atmosphere, and we have the nitrogen which is created in situ upon decomposition. For this way to fabricate the vapor cells, we have also a patent that was granted. So now coming in detail into the process flow, as already mentioned, we start with a silicon wafer of 150 millimeter diameter, 1.5 millimeter thick. Then we deposit oxide on both sides of the wafer. We make a first photolithography on the front side and pattern the oxide. And we use this double mask of photoresist and oxide to etch very deep trenches by deep reactive ion etching. We go up to about half of the depth of the wafer, to 750 micrometer. Then we remove the photoresist and deposit a thick aluminum layer. We do, in step 8, another photolithography on the back side, pattern the oxide, and use this double mask again to etch a 750 micrometer deep trench from the backside onto the aluminum layer. Then finally, in step 12, remove the aluminum, which makes all these central cylinders falling out. We remove the oxide, and then we deposit by ALD process an aluminum oxide layer, which acts as a diffusion barrier for the rubidium. Then in parallel, we fabricate glass wafers for the bottom glass and for the top glass. Here we start with, again, 150 millimeter diameter glasses, but of borough float. They are only 0.2 millimeter thick. We do a first photolithography with a lift-off resist, and then we deposit by thermal evaporation a thin layer of adhesion layer, a tantalum 10 nanometers and platinum 200 nanometers. So this is in the case where we want to have a resistive heater on top of the cell. Then we do a lift-off process, and we end up with the metallic pattern. We make an annealing to stabilize the resistivity, and at the end we deposit again by ALD process an aluminum oxide, again as diffusion barrier for the rubidium. For the top glasses, we have then some additional steps. We have again a photolithography on the back side of the glass here, and then we make a thermal evaporation of gold. So here we fabricate gold discs, and I will come to this topic just afterwards. We remove the photoresist with all the residual metal on it, and we end up with wafer having here the platinum resistive heaters and here gold discs on the other side of the glass. So after this, we make a first bonding. We have to align the wafers. Then we bond the bottom glass wafer to the silicon cavity wafer by anodic bonding. And this, what we call then a preform, we send out to an external partner who makes the dispension of rubidium azide diluted in water. And once we get it back, we align the top wafer on this preform, and we do another anodic bonding, which then takes place first under high vacuum, and then we fill back the chamber with argon to have the argon atmosphere inside. And now you see here in this configuration, gold disc, they are now sitting inside the chamber, and yeah, so this is the fabrication process of the atomic wafer cells on a wafer scale. So one issue in general with atomic vapor cells is that the rubidium has tendency to condensate on the glass window here, and if you shine then a laser through to probe the atoms, you get a light shift of the frequency, and this has a very high impact on the stability of the clock. Now in bigger glass-blown vapor cells, as we see it here, often this problem can be solved because the cells are quite large. You can heat them maybe locally here, and here in this example here, they have here the stem where they put the rubidium vapor in, and they just leave the stem, and this is then some kind of cold spot where all the rubidium will condense. So it will condense here and not on the cell window. This technique is much more difficult for a MEMS vapor cell because the dimensions are smaller. This cell here has dimension of 4 by 4 millimeter and a thickness of 1.9 millimeter. So obviously here is very difficult to introduce a temperature gradient. In the first activities to produce vapor cells many years ago, among other tests, we tried to bond the glass wafer onto the silicon cavity wafer by gold-gold thermocompression bonding. And when we analyzed the cells sometime later, we discovered there was no rubidium inside anymore. And when we looked more in detail, we discovered that all the rubidium was sitting on the gold seal. So indeed, there exists a binary phase diagram of gold and rubidium. As you can see here, there are several stable phases, and they have a very low eutectic temperature of, what is it, 34 degrees Celsius. So we thought if we can take advantage of this behavior, that gold and rubidium, they like each other very much, and we introduced here these gold discs inside the vapor cell. So this works very well, and it is based on two different mechanisms. On the one side, we have the Kelvin law. We don't want to go into detail of the formula, but it says that the vapor pressure of a droplet compared to the vapor pressure of a flat surface is inverse proportional to the radius of curvature of the droplet. So this means that small droplets, they have a higher vapor pressure than bigger droplets, and they will disappear in time. They will form a larger droplets, and all the small droplets, they will disappear. And on the other side, we have the law of Raoult, which says that the vapor pressure of each component of an ideal mixture of liquids equals the vapor pressure of the pure component multiplied by its molar fraction in a mixture, which means here, if we have rubidium on one side and gold on the other side, and we look at the vapor pressure, the rubidium has a vapor pressure, which is quite important at the temperature of operation, but gold has no vapor pressure. So gold will not evaporate, as you all know by experience. So if we have any mixture of rubidium and gold, the vapor pressure above this mixture will be lower than compared to the pure rubidium itself. And you see here quite well how this works. We have here a vapor cell just right after UV decomposition with the rubidium droplets sitting in the center of the glass. You see also in black here the dots around, which are the gold discs seen from behind. And now, as you do a thermal aging, 38 hours later, you have almost all rubidium in the center that disappeared, but you see that it went on the gold disc and it goes over the gold disc, so it's a little bit bigger than the gold disc itself. And if you continue this process after 286 hours, there is almost no rubidium left on the cell window, and all the rubidium is now fixed on these gold discs. So this technique is equivalent to have a locally lower temperature by maximum 2 degrees above the gold discs. And this is sufficient. This has not to be heated or powered or something else. This is constantly the case. It's always lower above the gold disc, so all the rubidium will go onto this gold disc, and there is no or only little rubidium that remains on the cell window and will impact thus the clock frequency. Remember that I mentioned on one of the first slides that we make a UV decomposition of our rubidium A site that yields metallic rubidium and nitrogen. And since for the application, particularly in clocks, we have to have a very precise ratio of argon and nitrogen partial pressure, we have to very well control the quantity of rubidium A site that we put into the cell. And we found here a very nice instrument from the company Symposium in Germany, the C-Flex arrayer. You can put here a whole wafer, and you have here the reservoir of the liquid or the aqueous rubidium A-site solution, and somewhere here is a very tiny nozzle, and this nozzle, I have here a bigger picture of the nozzle that ejects a droplet, has a volume of some 100 to 300 picoliter that are ejected per droplet. So with this dispenser or with this filling machine, we can very well control the quantity of rubidium A site that is spotted into each cavity. There's also a picture that is taken for every cavity that is filled. You see this here. So in this case here, we made the same filling for all cells, but of course we can also vary it, and we did this also, that we have zones of the wafer where we fill with less or with more rubidium azide. But typically we use 20 nanoliter of solution that we print into each cavity, and this corresponds, after decomposition of the rubidium azide, to roughly 1.3 microgram of rubidium in each cavity. Also, to control the quality of the printing, some test droplets are printed at the beginning and at the end of the process, and by pattern recognition they can calculate the volume of the droplet, and it is quite stable in time, so there's no big difference between the beginning of the printing and at the end of the printing. So once we get the wafers back from being printed, we have to do the final bonding. We do this with EVG 520IS bonding equipment, and I really want to emphasize that this is a standard bonding equipment. There was absolutely no modification done for printing, for fabricating these cells. The process itself is completely MEMS fabrication compatible. So here we insert the wafer stack with the preform down and the top glass on top, and the two are separated from each other with separation flags of about 500 micrometer thickness. So this allows us, when we pump down the chamber to 2 to the minus 5 millibar, we also have the same vacuum inside the cavities before being brought together in close contact. Then once we reach the required vacuum level, we make a backfill with argon gas in the chamber, about 120 millibar. Then we remove the separation flags, so the wafers, the glass wafer and the silicon wafer, they get in intimate contact, and we apply a voltage which we vary during the process from 200 to 600 volt to induce the anodic bonding. And typically we achieve a charge of more than 1,700 millicoulomb, which indicates a good quality bond. So here you see a wafer, 150 millimeter diameter wafer, that was realized in this process. In the case of these are cells for the atomic clocks, which measure 4 by 4 millimeter in size, and here we have more than 700 cells on one single wafer. Here we have a close-up of this wafer, and you see here quite well the resistive heater. One loop going back and forth with some contacts, because the backside has also to be contacted afterwards. And here you have the contacts to put the NTC temperature sensor on it. You see also quite well here these gold discs, but again they are not on the same surface than the metallic pattern, but they are inside the cavity. Within the project we also developed a fully automated equipment to decompose the rubidium azide into rubidium, metallic rubidium and nitrogen. You see here a motorized XY stage with a wafer on it. Then we have here in this box, we have a UV excimer laser which emits light at 248 nanometer, which is directed with these mirrors here onto the wafer. Here we have a laser diode which emits light at 795 nanometer, and which is used to make in situ measurement of the rubidium absorption. What we have here, we ramp the current of the laser, which changes its wavelength of the light, and as soon as you are on the right frequency for the rubidium atoms, you see a spectral line width that appears. In this instrument, in this setup here, we have also a high-resolution camera which takes a picture of every cell. And with this absorption spectra that I unfortunately can't show now, we can even have a first impression if the cell is good or if maybe there's a leak problem, because on the width of the spectral lines, we can conclude on the nitrogen pressure inside the cell, so we know also if the composition is already 100% or it's only part of it. Okay, but we also characterized the nitrogen partial pressure with a micro-Raman spectrometer that we have in our lab, and we established here a very nice protocol which allows us to measure, to make a non-destructive measurement of the nitrogen partial pressure. With the Raman, you can only see diatomic molecules, so we don't see the argon, but we see the nitrogen. And this was done in a way that we have a vapor cell that we dice in a way that it is completely open, and then we make a reference measurement just of air, and we know the composition of air and the amount, the partial pressure of nitrogen in air, and then we compare this to the measurement of the cell itself. And so from this measurement, you get a Raman peak intensity, which is generated by the nitrogen molecule. And this peak intensity is linear with the intensity of the laser, with the Raman cross-section, and with the pressure. And with this method, we do this always on some cells per wafer to have a quality control. We were able to measure the yield and the purity of the A site. So the A site, it's normally 100% rubidium A site, but there are also some other elements inside. There are other from the process to fabricate it, and the decomposition yield is never 100% neither. But here we could evaluate that for cells we do with rubidium, isotopically enriched 87 rubidium, we have about average yield impurity rate of 95%. And in the case of natural abundant rubidium A site, we have a yield of about 88%. If you look to the graph, what we did here, so we plotted the theoretical nitrogen pressure that we should have at 100% yield, and we looked at the measurement from the Raman spectrometer, and you see here, of course, this should be a linear line, and you see here, basically the value here, they said, you see here at 100%, we are only at 88% for the case of natural rubidium A site. If you look at the error bars, they are approximately 5 millibar, which is a very good value and which is largely sufficient to estimate the gas pressure. A very important part of the project was dedicated to lifetime estimation. I already mentioned rubidium is extremely reactive. And indeed, what you see here, if you put a cell with decomposed rubidium A site, so you have here the rubidium directly at the start, and you expose this to a temperature at 195 degrees, you see over time the small droplets disappear and form bigger droplets, and the bigger droplets disappear also. So we have to monitor the metallic rubidium consumption based on image analysis. And if we analyze these images, we can calculate a theoretical radius, assuming that the droplet is round. We have also measured the height of these droplets by white light interferometry. And with this both information, we can extract the volume per droplet, and knowing the density of rubidium, we know how much metallic rubidium in weight we have in the cell at the beginning and how this disappears over time. So this allows us to establish a consumption rate of the rubidium which is temperature dependent. So a very common way is to use the Arrhenius equation, which describes the temperature dependence of many chemical and physical reaction rates based on activation energy. So what we did here, we took the rubidium consumption rate that we measured before, and we did this at 3 different temperatures. And so we plotted here the logarithmic ratio in this Arrhenius plot, and then we can make an average. You can calculate. We trace a linear regression fit, and we have also here some confidence level, predicted interval that we trace here. And you see, since we make the measurement at high temperature, which makes the process going faster, we have error, or the confidence interval is smaller here than in the region of interest, which is completely normal. But with this, we could extract activation energy of these processes of rubidium disappearing of 67 kilojoule per mole and a huge error of 23 kilojoule, which is related to the fact that we have all the measurements here. Why we do the measurements here at 195 degrees, it takes roughly some months. Now we are currently doing measurements at 160 and also at 110 degree temperature, not measurement, but we make the aging at this temperature. And for example, at 110 degrees, the aging needed to extract the activation energy is more than 5 years. So this will allow us to design this regression fit smaller with a smaller error, and this is work that will ongo. So by knowing the activation energy and the temperature at which consumption rate was measured, we can calculate the consumption rate at the temperature where we want to use the cells, which is between 90 and 100 degrees. So if we look now at the histogram, which shows us the rubidium loss rate in micrograms per year at 195 degrees, we see that we have here the biggest peak here, which is in the interval of 1.2 to 1.5 micrograms per year. And from this consumption rate and from the relation I showed before, the temperature dependence, we can today say that we have a predicted lifetime of these cells of 16 years, but we have still a quite high interval of confidence with a lower limit of 3 years and the upper limit of 92 years. And these measurements of this thermal aging now at 160 and in particular at 110 degree will allow us to bring this predicted the confidence level closer together so that we have a little bit a better view on the predicted lifetime. So with this I come to the end of my presentation. At CSEM, we have manufactured various types of rubidium vapor cells which are used in the different maximal applications in the atomic clocks, magnetometers, the gigahertz and the terahertz imaging application, and also in the readback-based gas sensors. All this application and maybe also some photographs of the used cells will probably be seen in the afternoon sessions today. We made a huge progress in the quality control of the whole manufacturing process, and in particular in the decomposition process of the rubidium azide. The control of quantity was improved, and we have made extensive studies on the failure mechanism of the disappearing rubidium. So we were able to establish a model for the lifetime prediction. So thank you very much for your attention, and I'm open to questions if there are some.
Thank you for a very nice talk. I was wondering about the use of gold dots for collecting the rubidium. Is it important that they are dots, and then is it important that they are spaced equally in the way that you do them, or could you use a ring of gold and have the same effect?
So I would not recommend to use a ring because I showed you also the phase diagram, the binary phase diagram. So you have to know that the rubidium that makes the reaction with the gold is not usable anymore neither. So you have to reduce, or the quantity of gold introduced in a cell has to be below, very below the quantity of rubidium. So if you make dots, this is better than a ring. And the advantage of a dot is also that you can, in principle, design many small dots or a few bigger dots. But we have seen from the it was the Kelvin equation that you have, if you have a bigger drop, if you force the rubidium to take a bigger surface, the vapor pressure above this gold disk will be lower as if it would be small. So it is interest to have very few dots, but a certain size.
What's the lower limit on the number and size of dots that you could use?
I don't know. This was, I think we made two different designs, and this came up as a good solution also because we want really to have it at the site, and if you have, for example, two big disks, they will also take more place and reduce the through path of the laser, which we want to avoid.
Thank you.
Okay, we have some questions from the chat. So we have Ilya that asks, why argon and not neon as a buffer gas? Do you want to answer, or do you want to ask?
Yeah, maybe I give the answer to you. I mean, I was the guy who was fabricating the cells, and I did this upon request. So, Jacques.
So the argon, this is specific for the clocks. So somehow there are temperature sensitivities induced by the buffer gas. So we need a buffer gas, and we need to compensate for the sensitivities of these buffer gases. One is positive, one is negative. So that's why we have nitrogen coming from the rubidium azide, and we have to compensate with another gas with the opposite sign, and argon has an opposite sign. That's why we are using argon. I hope with that I answered your questions, but then he asked other questions, Ilya. The question is, how about influx of gases into the cell, H2 or helium?
Influence, you said.
So I think he thinks about are either hydrogen or helium going inside the cell or outside the cell. I think this is the question. How do you handle the fact that we might have permeation of gases inside the cell?
Well, I mean, for this we do all this lifetime stuff, evaluation of the lifetime and so all this, I mean, all the different components that influence the lifetime somehow are put together in this estimation.
We have also internal coatings.
We have a coating, but which is more to avoid diffusion of the rubidium into the glass in particular. But it's clear that, well, before the bonding, we heat, extensively heat the preform with the rubidium azide already inside to 320 degrees, 350 degrees for a long time, so that we can evacuate all the trace atoms, molecules that are sitting on the surfaces. But we have an anodic bond, which is leak tight in principle, but of course, leak tight doesn't mean anything. I mean, there's still exchange of, for example, with helium. Yeah, I know you can measure this, but it's very, very low.
Okay, then we have Tom that asked a question. Are you able to comment on the resilience of the cells to the induced environment? For example, vibrations. Do vibrations influence the performance of the cells, or how do they react to vibrations?
I have no idea. What we tried is I think we did this some years ago with some cells in a kind of a shaker, and we wanted to see if the droplets they remain on the gold discs. And this was the case, so they didn't move due to the vibration.
Okay, and there are also tests done in the clocks. For sure, the environmental testing of the clocks, they have different aspects, and one of the aspects are the vibrations, and we have to comply with the launch of the rocket or other things if we have space applications. So we do also vibrational tests for the clock, so this is a system where the cell is integrated. Then we have a question by Ilya again. Was there an option tested with anti-relaxation coatings as, for example, ODTS?
No, this was not done. We have always to be compatible with our fabrication process, which involves anodic bonding, and this has to be done at a higher temperature, clearly above 300 degrees, and all relaxation coatings that cannot withstand this temperature, they are out.
Good. Then we have a question by James. It's good to see all these people on the chat. Thanks. Is there a mechanism that would enable the gold dots to be used for density regulation, sourcing and sinking from vapor to condensed spots?
As far as I understood, this vapor pressure increase or decrease above the gold disk is as a local phenomenon, so you will not influence the overall pressure inside the cell. So I don't see how you can use this, but it's an interesting idea, maybe.
Okay. If we do not answer your question, then you have to re-ask them on the chat or make a comment on the chat. Then we have a question by Nathanael. Regarding lifetime, I have a couple of questions.
Yes.
1. Have you observed loss of hermeticity of the cell over time or temperature?
No.
2. This is simple question. Simple questions, simple answers. But this means we have good cells and good bonding. Do you have measured data from a live test example, Mach level? I'm not sure if I understand the question. So basically, can you comment on the lifetime estimation that we did for the cell? I think you explained that during the talk, but perhaps if you can make a summary of what we did and why we did that, and what do we expect from the lifetime test that we did.
Okay, yeah, so yeah, we evaluated the lifetime of an average of 16 years. But there's a huge error on the interval of confidence, which will hopefully soon be closed. Can you maybe repeat the question? Do
you have measured data for live tests?
So yes, we make this thermal aging, thermal accelerated aging. I almost can't speak of accelerated anymore because it takes years. But we have indeed cells. We evaluate the quantity of rubidium with the method I presented, and at a certain time there is nothing left anymore. There's no spectroscopic signal anymore, and then we know it all disappeared. So yes, we did this at elevated temperature, which makes that these processes going much faster, and with the Arrhenius equation, that's the reason why we apply it. We can calculate at what loss rate we have to handle at another temperature, at the temperature of operation of the cells.
Yes, and if I just can comment, so Nathalie asked for the MAC, for the multi-atomic clock. Sure, the lifetime that requirements are at least 10 years, and the goal is to reach these requirements. That's why we are doing this accelerated aging. For sure, if you measure the clock signal as we did with the atomic clock, we see the drift performances of the cell, which is improving with time. So the drift is getting lower and lower to a level close to 10 to the minus 12 per day. And with that, these are the life tests. I don't know if this answers the question, but these are all tests we are doing with the target to ensure this 10 years lifetime.
Maybe just to mention that the numbers I gave with the 16 years and the 3 years and 92 years, all these three numbers are the most pessimistic assumption that you can make.
Good morning, everybody, and thank you for joining this symposium. And my apologies for the technical problems during the presentations up to now. We'll try to fix this during the lunch break. So my talk today will be about rubidium xenon vapor cells for miniature atomic gyroscope studies, and this was work conducted at the University of Neuchâtel together with our partners at Bosch in Germany. So the outline is the following. I'll give a short introduction why this is interesting, then report on the cell design and cells characterization, and present some preliminary NMR measurements without spoiling too much of the suspense for the talk given by Bosch this afternoon. So the introduction motivation is that drift-stable inertial sensors are key enablers for the applications like highly autonomous driving cars, notably for helping them keeping straight on one lane of the road without going onto other lanes in autonomous mode. And for this NMR-based, so nuclear magnetic resonance-based atomic gyroscopes based on rubidium xenon vapor cells can offer 50 times enhanced bias drift stability compared to the mechanical MEMS gyroscopes that you might have in your cell phones. So here is a photograph of a demonstrator physics package unit of such a atomic gyroscope by Northrop Grumman from the US, and the height of this physics package is about 3 to 4 centimeters, and it's using microfabricated cells, and we've been doing so a variety of small centimeter scale glass-blown vapor cells in order to enable studies on these systems. And here I will present on the characterization of these cells using atomic clock spectroscopy in order to get some precision measurements of the gas content in the cells and to demonstrate their use for the gyroscope developments. So very shortly, the principle of an atomic gyroscope, it's based on Larmor precision and readout. And there we look at the precision of a xenon nuclear spin around a magnetic, so it's magnetic moment of this xenon around a static magnetic field that is external. And if the external magnetic field rotates, because the whole sensor rotates, this will become visible as a shift in the measured Larmor frequency of the xenon. And this can be read out via Faraday rotation using a probe beam interacting with rubidium atoms. So why rubidium atoms in addition to the xenon? So the scheme of detection is the following, that you cannot directly optically pump the spin of the xenon. So that's why we turn to optically pumping of the rubidium atoms held in a cell together with the xenon. And if we pump the rubidium, that's the red balls here, we align their spins while the xenons are still unaligned, so arbitrarily oriented. Then, due to collision, the rubidium atoms will transfer their spin to the xenon, and the xenon will become aligned and produce a magnetic moment. And then we can drive the Lamarck precision of the xenon around the static magnetic field. And then if they, in turn, do their precision, this precision can be transferred, can be sensed as a magnetic field by the rubidium atoms, and this can be read out with a laser beam. In order for all this to work, we still need to preserve the xenon spin and the rubidium spin inside these small cells, and this necessitates that we add, in addition, a buffer gas, so an inert gas, to these cells, so we will have at least a 3 or 4 component cell content in these vapor cells. This brings me to the cells we did in this study. So here you can see the design of 4 different cell shapes that we developed. The bodies were made of borosilicate glass, and we have a high cylindrical, a flat cylindrical, a cubic, and a spherical cells, where we aimed to having up approximately the same volumes inside there, and we performed these cell filling and production in our facilities here at the university. And down here on the right, you can see the final cells produced with the rubidium and the vapors. What is inside is 87 rubidium and some 360 millibars of buffer gases, and there we used roughly 190 millibars of an argon-nitrogen mixture. And there, the reason for using this mixture is, once more, we want to do clock measurements in order to characterize the contents, and there the temperature sensitivity of the clock transition due to this mixture of buffer gas is strongly reduced around the operation temperature. And we add 170 millibar of natural cesium around, and this will be then in the gyroscope applications the sensor for the rotation sensing. Now, in order to characterize these cells, we turn to CPC spectroscopy on the rubidium clock transition, and the clock transition is connecting the 2 lower hyperfine components of the rubidium ground state here, which is at 6.834 and some other digits gigahertz. And we can then sample this by a bichromatic laser light that we produce by modulating a laser beam using an electro-optic modulator. And this transition is then sensitive to the gas content in the cell due to rubidium buffer gas collisional shift, and we measure the collisional shift of this clock transition. Here you see a plot of our signal against the microwave frequency, and we get a very sharp discriminator that allows us Hertz level resolution at 6.8 gigahertz absolute frequency. Now, this transition is frequency that we measure here, that we plot vertically here, unfortunately is sensitive to light shift, which means if we vary the optical light intensity here, we get some dependence of the frequency. So, of course, we need to correct for this, and we extrapolate to 0 light intensity in order to conclude on the light shift corrected collisional shift of the rubidium transition, and from this we can get information on the total gas pressure, and we find values between 350 and 358 millibars around, which is right close to the expected 357.7 millibars due to the mixtures we put inside. Now, in addition, this frequency we can then measure as a function of the temperature of the cell. And this also gives us some dependence, and this dependence allows us then to infer the gas mixture if the temperature shift coefficients are known. And these are known. Here is the well-known theory that you can find in the Vanier-Audouin book on atomic frequency standards. So the frequency shift, it's just the pressure multiplied by an expansion of a second-degree polynomial around a given temperature of reference. And there's the beta, delta, and gamma coefficients that represent the total shift of our frequency. The delta, a linear coefficient of temperature, as it is shown here in this example. And then you maybe have a quadratic coefficient, which usually is much smaller. And each of these coefficients can be composed as a weighted average of the pure gas coefficients if you're looking at a mixture. Now, these coefficients, they are quite well known for nitrogen and argon, as you can see here. But for xenon, they are much less common to measure, and actually there's only the absolute pressure shift, which is reasonably well known. And there are kind of diverging predictions and estimations for the temperature shift, the delta, and there's absolutely no data on the quadratic shift here. So but by fitting with the available data and this second-order temperature model, we can extract from our cells a value for the delta coefficient for the xenon, which is around minus 0.35 Hertz per millibarad Kelvin. So this is in reasonable agreement with the previous estimations and predictions that are available in the literature. So from these cells, in addition to looking at gyroscopes, we could also extract some basic physical parameters. Now looking at NMR measurements, here's some first results that were realized by the Bosch team in Germany. And they show us the xenon-free induction decay in a gyroscope setup with using a single beam only and no RF drive. And from after the polarization, we can see here a ring down of the signal detected via the rubidium laser interaction, as described before. And we get a very long relaxation time, T2, of this xenon spin of 20 seconds, and that's very helpful in order to do the gyroscope developments. And if we then do a Fourier transform of these ring down, we can extract the frequency of that signal, and we get here at this applied magnetic field, we get a very, very clear xenon 129 signal, and it is the shift of this frequency that later then will be used in order to detect the rotation of the gyroscope. And this was done by the development steps at Bosch. So in conclusion, we had successful fabrication and filling of our custom-made rubidium Siemens cells for the NMR gyroscope studies. And we could do the spectroscopy on the 87 rubidium optical and clock transitions to confirm the expected gas content in the cells. And the first experimental estimation for the temperature shift coefficient that we could extract from these cells on the delta coefficient for the xenon and the rubidium clock transition in xenon gas is quite interesting and to see, and it coincides with the expectations and predictions from other publications. And with this, we could hand the cells over to Bosch for the gyroscope studies and developments. And with this, I thank you for your attention, and of course, I'm open for questions.
Now there is one question by Ilya on slide 9. If you could go back to your slide 9.
Yep.
Is it 5 Hertz or 5 kilohertz?
It's 4 Hertz, yeah.
It's Hertz. Simple question, simple answer.
Can you say something about the role of the cell geometry in the gyroscope experiments?
Well, yes, there's some reports about different geometries that are more appropriate, especially this is typically linked to the amount or to the existence of quadrupole splittings in the gyroscope signals. And quite often the spherical shape of the cell is desired, because then also if you have impurities in the cell, you have a spherical geometry, and then you expect that these impurities, the effect of these impurities should cancel out. So, but unfortunately, if then you want to go to MEMS cells, then it's much more difficult to realize spherical cells with the technologies that Thomas had just presented. So that's why we wanted to try more different geometries that are more easy to realize with MEMS technologies then.
So there was a comment on the answer from Ilya, so a comment to Morgan. There is a nice paper from Mark Limes on the geometry. Then we have a question from Emmanuel. What would limit T2 star here? The fact that the cell is cubic?
I would not expect so. I think the T2 star should probably mostly be limited by the buffer gas fill. And so if we don't put any buffer gas into the cells, you can easily imagine that the atoms, the xenon and the rubidium, just do ballistic flight inside the cells and bump into the cell walls every millisecond or so. And this completely depolarizes the atoms, and that would be a 1 millisecond relaxation time then, a T2 time. So we need to put sufficiently gas inside that the relevant atoms for the interaction and for the measurements, so the xenon and the rubidium, are efficiently localized and ideally never go to the walls. But they will decohere also due to the other collisions with the gas and among each other.
Okay, thanks. Then we have a question which is also related to the shape. I think we can orient the question towards the paper, but the question was, are there advantages of cells with different shapes?
So this was exactly the goal of why, that was exactly the motivation why we were looking at different cell geometries to find this out. But at this moment, I don't think we have sufficient data to answer on these questions based on our cells.
Okay, then I think it's on the slide which is now shown. At which temperature this FID was measured?
So thank you, Janine. So Janine from Bosch answered for me. So it was measured at 90 degrees Celsius. Thank you.
Then we have a question. What about composite pulses to boost the spectroscopy?
Okay, at this point, you can also, of course, you can always go further in the precision. Okay, I guess this rather refers to the clock measurements. At least I understand it in this sense. Of course, you can always do fancy measurements and things in order to increase the resolution. If we're looking here at our error bars, I don't think that we are really limited at this level by the resolution of our spectroscopy. And I should also add that here we selected CPT spectroscopy of the rubidium transition because it is relatively easy to implement and can be implemented also on cells of different size and shape. So we stayed flexible for testing different cell geometries. So we didn't pursue further in order to optimize, let's say, clock operation.
So many thanks, Christoph, for all these answers and for the nice talks of today. We are at the end of the session now.